Thank you for inviting me to give this lecture in honor of Daniel J. Raskin. It has been 55 years since I first stepped onto the Johns Hopkins campus as a postdoctoral fellow. It would be fun to be there with you today, but I understand the need to avoid the risk of COVID. Today I'm going to review recent research on ambient temperatures associated with injury mortality and other risks. I will pause a bit when I change slides to give you a chance to view them. Life on Earth is sustained by energy from the sun and atmospheric gases that keep that energy within a range conducive to vegetative and animal evolution and sustenance. Gases such as carbon dioxide and water vapor are called greenhouse gases because they, along with the sunlight, support photosynthesis in vegetation. The vegetation emits oxygen required for respiration in animals, including Homo sapiens, as well as providing food for their sustenance. Compared to the atmospheres of other known planets, Earth's greenhouse is unique as far as we know. But we do know that it is in danger. In his most recent book, Jared Diamond notes that nuclear winter and global warming are the existential issues of our time. The word existential is often used too loosely, but the fossil and geological record indicates that periods of extreme cold or extreme heat wiped out much of the life on the planet on 5 occasions in the past. This time, the potential for both is mainly human-caused. Fortunately, we have no data on nuclear winter. Based on knowledge of the effects of soot and dust from volcano eruptions, simulations indicate the effects of the soot and dust from a major nuclear bomb exchange among 2 or more of the nuclear powers would block solar energy for years after millions, perhaps billions of humans had already died or been maimed from explosions and radiations. Temperatures would drop as much as 20 degrees Celsius in the U.S. and 35 degrees in East Europe and Asia. These temperatures would be hugely lower than the drop in temperatures that caused the ice ages historically. Precipitation would decline an average of 45%, vastly reducing food production. This graph is based on simulations by A.L. Robach and his associates at Rutgers University. It shows expected temperature changes in Iowa 3 years following a large exchange of nuclear weapons explosions. The purple indicates temperatures if a third of nuclear weapons in the U.S. and Russian arsenals were used, and the orange if all of the weapons were used. The agricultural output of the state would be virtually wiped out. This is typical of what would happen to temperate regions around the world, but most grievously in the Northern Hemisphere. The 2 major nuclear powers, the U.S. and Russia, have more than 6,000 nuclear warheads each, dwarfing the hundreds extant in other nuclear powers. The latter nations are dangerous because some are in the hands of countries whose belligerence could trigger the involvement of 2 leaders in weaponry. Donald Trump recently abandoned the nuclear weapons treaty with Russia that limited the number of weapons each could have available. Vladimir Putin quickly followed. Scientists should take every opportunity to emphasize the dire consequences of nuclear weapons use. The other existential environmental hazard is global warming. I'm sure that you're all aware that the planet's atmosphere, oceans, and lakes are warming due to the accelerated use of fossil fuels, particularly during the past 150 years. This growth has initiated amplifying feedback systems that threaten to accelerate warming even further. Most media reports on warming suggest that the effect is gradual and linear. However, amplifying feedback leads to an acceleration of change in the phenomena in question. Burning fossil fuels has increased the risk of 3 major amplifying feedback effects. Increased heating of ocean, river, and lake waters results in more evaporation of water molecules that retain heat, leading to more evaporation. The cloud formations that result reflect some solar radiation so that the effect is moderated. The albedo effect occurs when the ice sheets and glaciers melt to reveal darker surfaces that absorb more heat that in turn melts more ice. The Arctic tundra contains enormous amounts of carbon dioxide and methane. If it melts and those gases are released, warming will accelerate melting more tundra to a point where the process is irreversible, called the tipping point. In addition to human use of fossil fuels that heat the atmosphere and oceans, setting these feedback systems in motion, there are behavioral feedback systems such as the use of air conditioning powered by fossil fuels that increase warmth, leading to more use of air conditioning. An additional behavioral feedback effect is likely occurring because of a warming effect on motor vehicle use. More vehicle use in warmer weather increases carbon dioxide emissions that produce more warming. My interest in this phenomenon was piqued by what I think are mistaken claims about the reverse trend in U.S. road deaths 5 years ago. With some annual fluctuation, yearly road deaths in the U.S. during the past 50 years declined due to a variety of vehicle, behavioral, and environmental changes that I will mention in more detail later. In 2015, the downward trend in death rate per 100,000 population abruptly reversed, increasing by 7%. Later, we learned that it increased again in 2016. When the 2015 data were released in 2016, safety officials at the National Highway Traffic Safety Administration and others interviewed by the New York Times attributed the reversal to the cause du jour, increased distracted driving by those using cell phones and other electronics. That didn't make sense to me because those devices were in widespread use before 2015. Indeed, NHTSA's observational surveys showed no jump in drivers' use of electronic devices in traffic during 2015. Handheld cell phone use declined a percentage point from 2014 to 2016, part of a downward trend beginning in 2012. Headset use and observable manipulation of handheld devices changed little. So I asked myself, what else happened in 2015 that could increase road deaths? For one thing, the average temperature in the U.S. increased an average of 1.5 degrees Fahrenheit or 0.83 degrees Celsius from 2014 to 2015. We have known for decades that miles driven and road deaths are higher in warmer months and lower in colder months. Here we see about a 20% variation in miles driven from February to July, year to year. The gray areas are economic recessions. Travel peaks in July and is at a minimum in February. This slide from a National Highway Traffic Safety Administration report in 2005 shows road deaths by day of the year from 1975 through 2002. Exclusive of holiday peaks, historically there were more than 1,000 more deaths per day at the summer peak compared to the winter low. The distribution parallels seasonal variations in temperatures, so it is not just a summer travel phenomenon. But as we shall see, parallel trends in time can be misinterpreted. A more refined analysis is required to test the hypothesis that warming was a factor in the 2015 reversal of death rates. I hypothesized that the increase in deaths in 2015 was associated with increased driving related to the temperature increase. Since temperatures and precipitation vary from day to day and are different among local areas, I looked for daily data on local miles driven and vehicle deaths in local areas, as well as temperatures and precipitation. Since the Federal Highway Administration reports miles driven among urbanized areas and deaths in the Fatality Analysis Reporting System indicates the county of deaths, I assembled two data sets of daily temperatures and precipitation, one including miles and one including road deaths. The files contain data from urbanized areas with populations exceeding 300,000, and the road death file was limited to the 100 most populous counties to avoid instability in data based on smaller numbers. The data on miles driven indicated about 59.5 miles per year on average per person for each degree Fahrenheit increase in temperature. That may not seem like much, but the 1.5 degree average Fahrenheit temperature increase that occurred from 2014 to 2015 would add almost 13.6 billion miles of travel in the urbanized areas studied. The mileage data suggested an additional amplifying feedback on warming may be occurring. More warming leads to more miles driven and more carbon dioxide emissions that in turn contribute to more warming. To obtain the road death rates per billion years of population exposure to specific average daily temperatures shown in this slide using the fatality analysis reporting system data, I first added up road deaths that occurred on days of the shown average temperatures. To find the number of people exposed to those temperatures, I added up the estimated populations of the counties each day that the temperature averaged the indicated degrees and calculated the death rate per people exposed. Notice that the death rates are strongly related to daily temperature, more than doubling from below freezing to the mid-80s Fahrenheit, and then reverse slightly at the highest temperatures. It is unlikely that small increments in temperature affect driver use factors, such as inattention, alcohol use, etc. Given the relation between temperature and miles driven, the most likely explanation is that discretionary road use is influenced substantially by relatively small increments in ambient temperature. Although we do not have data regarding road use by pedestrians and bicyclists, the lack of protection from weather for them makes such an explanation even more likely. In epidemiological terminology, warming results in increased exposure to road death risk. I did a logistic regression of temperature and other factors in 2014 to see if the correlation held, controlling statistically for other factors. In addition to temperature, the greater risk was also associated with more precipitation, higher speed limits on urban freeways, geographically larger counties, and lower average incomes, but these did not modify the temperature effect. Using the equation based on 2014 data, I estimated the expected deaths in each county during 2015 if temperatures had remained the same on a given day as they were in 2014. Added across all counties, there were a total of 600 more deaths than expected related to the 2015 temperature increase. This 6.2% increase is just short of the 7.1% increase in deaths observed nationally. I also calculated the expected deaths in 2015 if all urban freeways in the counties studied had a 55 mile per hour speed limit, the lowest among the counties studied. Results suggest a reduction of 20% in deaths from the actual number would have occurred from reduced speed limits even as temperatures increased as much as they did. Speed still kills, whatever the weather. When the study was reported in the press, a spokesman for the AAA Foundation was quoted saying that the 2015 increase in road deaths was likely a result of improvements in the economy rather than warming. There's a long history of studies relating fluctuations in road deaths to fluctuations in economic indicators. None of these studies that I have seen test the validity of their models by a split-half design. The most recent of these, by Charles Farmer, regressed time series of deaths on time series of unemployment, the log of miles driven, and calendar year from 1990 through 2015. Mr. Farmer did not use all the data available, so I did so, and estimated the parameters in his model using the first half of the data. This slide shows the coefficients in Farmer's model and the model applied to the first half of the whole data set back to 1976. Notice that the signs reverse on the coefficients of calendar years and logarithm of miles driven. This happens because the two variables are so highly correlated that the coefficients are meaningless. The negative coefficient on unemployment suggests that deaths are higher when unemployment is low, but why would they be twice so in the first half of the data compared to the period Farmer used that included the Great Recession of 2008-2009? This slide shows the fit of the first half model to the full data set. The actual deaths in the second half are not predicted by the model. Deaths did not increase as unemployment declined after the Great Recession and only increased in 2015-2016 when the temperature increased. The model is less than worthless. It is misleading. To get a better estimate of the temperature effect on mileage and deaths nationally and control for risk factors in addition to unemployment, I explored the possibility of using monthly data among U.S. states. Since temperature can vary substantially within states and months, I was concerned about the loss of fidelity using available average monthly temperatures among states rather than local areas by day. I first counted the number of road deaths in each of the lower 48 states during months with a given average temperature, and the number of people in those states when the average temperature was at a given level, and produced a graph similar to that shown in earlier for local areas. The correlation of death rates to temperature held, but with more variance. Since the numbers are large enough using monthly data to examine important subsets of the data, I looked at the correlation of temperatures with deaths of occupants of cars, trucks and buses, and separately motorcyclists, pedestrians, and bicyclists. For population potentially exposed, deaths of motorcyclists and pedal cyclists are rare at average monthly temperatures below freezing, and increase as temperatures rise above that point, then level off at temperatures in the 60s, 70s, and low 80s. But pedal cyclist deaths decline a bit at the highest temperatures. Vehicle occupant deaths other than motorcyclists gradually increase on average as temperatures rise, but accelerate in the 70s and 80s. The trend in pedestrian deaths is less pronounced. I added several control variables in a logistic regression model using the state data. In addition to temperature, precipitation, and unemployment, I included liability insurance expenditures, gasoline prices, number of registered vehicles, percent of registered vehicles that were motorcycles, buses, and trucks, and the median age of the population. The choice of variables was informed by previous research. That research indicates that pickup trucks and truck-based sports utility vehicles that are heavier than most passenger cars increase the deaths of occupants of other vehicles and have higher rollover death rates than passenger cars because of too high a center of gravity relative to track width. Motorcycles have a death rate 34 times that of other vehicles for miles traveled. Trucks, buses, and motorcyclists kill more pedestrians per mile driven than passenger cars. Research on the introduction of required liability insurance by states in the 20th century correlated the requirement with an increase in road deaths, inferring that insured passengers and drivers were less cautious. Road death rates fluctuate inversely to gasoline prices. To test the consistency of model years year to year, I fitted the model to state data for each year separately from 2000 through 2016. The detailed results are too numerous to display in a slide, but the most consistent results can be summarized as follows. There were higher death rates related to warmer temperatures, more trucks as a proportion of all vehicles, and an older population. Deaths were higher when unemployment was up, except after recessions. There were lower fatality rates in states with higher insurance costs and higher gasoline prices. Using the logistic regression equations, I estimated the changes in deaths that would be expected in 2015 if each of the variables was unchanged from 2014, while the others changed, and in 2016 if each of the variables was unchanged from 2015. For each of the predictor variables, I substituted the 2014 value in the equation, leaving the others at 2015 value for that year, or the 2015 value in the 2016 equation. The sum of the predicted deaths among states, shown in this slide, was compared to the actual deaths to estimate the number of deaths that occurred related to the change in prevalence of a given risk factor, corrected for the status of the others. The average annual temperatures among the states in this study were 51.1 in 2014, 53.1 in 2015, and 53.9 in 2016. About 5.3% more deaths than expected were related to increased temperatures in 2015, and 3.7% more in 2016. Reduced unemployment in 2015 was associated with more than a 7.2% less predicted deaths than actual deaths in 2015, and 1.5% less in 2016, contrary to the economic hypothesis. Increased percent trucks of all registered vehicles were related to a 3.6 and 4.3% increase in deaths in 2015 and 2016, respectively. Reduced gasoline prices were associated with a 12.6% increase in deaths in 2015, but an increase in prices related to a 1% decrease in deaths in 2016. Deaths declined somewhat from expected relative to increased insurance expenditures, 1.5% in 2015 and 0.5% in 2016. One of the likely reasons for the difference in correlation of lower unemployment with lower road deaths is the variation in new car sales with economic conditions. I could not find new car sales state by state, but nationally new car sales vary inversely with unemployment as seen in this slide. At least part of the correlation of unemployment and road deaths is likely the increase in newer, safer vehicles on the road as the economy improves. I also looked at temperature and miles driven per vehicle among the states in 2014, 2015, and 2016. The least squares regression of miles driven per vehicle registered indicated 117 more miles driven per degree of warmer temperature in 2014, 137 in 2015, and 145 miles in 2016. When precipitation, unemployment, insurance costs, and gasoline prices were added to the equation, they were not significantly related to miles driven per vehicle. Again, it appears that warming temperatures contribute to increased driving, more emissions, and increased warming in an amplifying feedback cycle. Given the documented effectiveness of numerous injury control efforts, as well as effective temperature and types of vehicles on road death rates, I wondered how many deaths would have occurred as a result of temperature changes and vehicle growth during the past 50 years without any injury control efforts. Consider what we know about injury control effects. Combined lap and shoulder belts reduce vehicle occupant deaths by about 45% when used. Belt use increased from 15% before laws requiring belt use were enacted in the 1980s to more than 88% recently, based on observed belt use by vehicle occupants. Alcohol at 0.08% or above by weight in U.S. drivers in fatal crashes declined from 35% in 1982 to 20% in 1997, rose slightly, then dipped to 20% again in 2005. This reduction was associated with changes in state laws such as the legal minimum drinking age and the lowering of the legally acceptable blood alcohol concentration. Licensed teenage drivers are involved in fatal crashes about 3.5 times as often per mile driven as 30 to 70-year-old drivers. Reductions of 16 to 21% of 16-year-old drivers' fatal crashes were associated with laws restricting the conditions under which 16-year-olds could be licensed, the percent reduction dependent on the specifics of the restrictions. The involvement of drivers 16 to 19-year-old in fatal crashes declined from about 50 per 100,000 people in that age group in the late 1970s to fewer than 20 per 100,000 in 2014 due to additional declines in licensure. That was also perhaps affected in the 1980s by the discontinuance of driver education in many high schools. Research in the 1970s showed that driver education increased licensure without reducing the risk of crashes of those licensed. Reduced licensure is also associated with increased insurance rates. Cars that met the initial federal safety standards required of new vehicles sold to the government in 1966 models and all cars in 1968 and subsequent models had 40% fewer occupant deaths per vehicle than previous models. Manufacturers phased in airbags as standard equipment in new cars during the late 1980s as a result of a federal standard for increased frontal crash protection in new passenger cars. Manufacturers also installed side airbags and improved energy management of other vehicle components in numerous makes and models in subsequent years. The effects of these installations is reflected in energy transfer to crash dummies in the government's vehicle crash test, which steadily improved year to year through 2010. A study of 1999 through 2005 model years of passenger cars, minivans, and sport utility vehicles assessed the effects of each of the various vehicle safety features, controlling statistically for the effects of the others. Vehicles with electronic stability control had about 42% fewer fatalities and crashes per vehicle than vehicles without the system. Electronic stability control installations increased from 29% in light vehicles of the 2006 model year to 71% of the 2011 model year, after which all new vehicles were required to have them. Vehicles that had injury criteria above the average on the government side crash test had 19.4% fewer deaths. Those that scored best on the Insurance Institute for Highway Safety's offset frontal crash test had 8.6% fewer deaths. A review of studies of alteration of the built environment to reduce pedestrian deaths indicate effects from 25% to 75%, but the extent that these measures have been deployed in the U.S. is unknown. States that implemented statewide trauma response systems had about 9% lower fatality rates on average, controlling for other factors, than states without such systems. Because of overlapping effects, these percentages cannot be added together to assess their collective effect. An example of overlapping effects is seatbelt use in driving while intoxicated. Intoxication is associated with a lack of belt use. Nevertheless, given these known effects, the downward trend in death rates should have been much steeper than what we see in the gross trend. To estimate the deaths that would have occurred without these injury control efforts, I did a logistic regression analysis of the deaths per population in the 48 contiguous states during 1961, which was before the implementation of the injury control interventions that I mentioned. The odds of death were substantially correlated to temperature, precipitation, vehicles per population, and types of vehicles in the mix, as well as the median age of the population among the states, similar to the results 40 to 55 years later. The major difference is the reversal in the coefficient of median age, which is likely the result of the reduction in teenage licensure. I then applied these coefficients to each state during each of the years 1962 through 2015 and summed the expected deaths for each year to get the total deaths expected from fluctuations in particular variables without injury control efforts. This slide shows the results compared to the sum of the actual number of deaths in those states in those years. The equation predicted slightly fewer deaths than occurred in 1962 through 1966, indicative of a conservative estimate of effects, but predicted deaths increasing rapidly relative to actual deaths in subsequent decades, except during the 1980s and 1990s. In those years, the baby boomers were leaving their higher risk years, and motorcycle registrations declined dramatically. By 2015, the deaths expected without interventions were 8.8 times the actual number of deaths. The model predicted about 8 million deaths during 1968 through 2015, but 2.2 million occurred, suggesting that about 5.8 million road deaths were avoided by the preventive efforts. I should note that much of the adverse temperature effect during this period was not from rising temperatures, but due to migration from states with relatively cooler temperatures to states with warmer temperatures. But rising temperatures do not portend well for the future of road safety. Also, recent research indicates that rising temperatures may increase the risk of non-transport injury mortality as well. The literature also suggests altered behavior related to pollution, which is high in Chinese cities. I and my colleagues Lian Zhao and Kai Chen recently published findings regarding fatal injuries in relation to pollution and temperature in 9 cities in Jiangsu Province, China, during 2015-2017. The Jiangsu Provincial Center for Disease Prevention and Control provided us with daily injury death counts that we supplemented with data from other sources. These are the annual deaths per million population in the 9 cities from 2015 through 2017. The Chinese city with the lowest rates, Nanjing, had rates about 4 times the U.S. national rate, and in some years the cities with the highest rates were about 10 times the U.S. rate. As in the previous studies I discussed, we aggregated the injury data by daily temperature, as well as the number of people in the populations of the cities on days that the temperature was at a given level. This slide shows the relation of maximum daily temperature to transport deaths, about 90% of which are road deaths in China generally. The temperature scale is Celsius, so 0 is the freezing point. Less than 0.5% of days had a temperature below freezing, so residents of these cities are dealing with a substantially warmer climate overall compared to the U.S. There's little evidence of a correlation of transport fatality rates to temperature except for the decline at very hot temperatures. 40 degrees Celsius is about 104 degrees Fahrenheit. This may be due to reductions in bicyclist deaths as we saw in the U.S., but we do not have data from China on the vehicles involved. In contrast, the rates of unintentional injury deaths other than transport declined slightly up to about 25 degrees maximum daily temperature, accelerated upward at higher temperatures, and did so extraordinarily at temperatures above 34 degrees. These nonlinear patterns led us to the decision to analyze the data separately for cool temperatures, that is, those less than 25 degrees, moderate temperatures, those 25 to 34 degrees, and hot temperatures, 35 plus degrees. We did a Poisson regression of the effects of temperature, precipitation, and pollution, as well as other factors. The outcome variable is the death count for each day in each city during the 3 years. The average deaths per day for each city were 3.2 due to transport injuries and 4.4 due to other injuries. We took the log of population and included it as an offset variable to correct for differences in population size among the cities. In addition to daily temperature and precipitation, we included ozone pollution in our study as an indicator of air pollution that has been shown related to altered daily activities and is quite pronounced in these cities. Also, we control statistically for injury deaths on weekends and holidays to correct for the effect of likely different activities on those days. We took the square root of precipitation and the logarithm of ozone to reduce the skew in the distributions. Nanjing was also included separately as a predictor variable. Since its average values on the other predictor variables were within the range of those of the other cities, its relatively lower injury rates are unlikely a function of these factors. The numerical results are too complicated to display on a slide, so I will summarize the significant findings. Corrected for other factors, transport deaths were related to warmer temperatures when they were less than 25 degrees Celsius, but the correlation reversed at higher temperatures. Non-transport injury deaths increased substantially with higher temperatures when temperatures were in the 25 to 34 degree range, and even more so at temperatures 35 degrees and higher. Deaths were lower on rainy days when temperatures were cool and moderate, except for non-transport injuries when temperatures were moderate. Higher ozone concentrations were associated with more deaths, except when temperatures were low. Transport fatalities were consistently lower on weekends and holidays at high and low temperatures. Other injury deaths were higher on holidays when temperatures were low to moderate. These results are mostly consistent with previous studies showing an increased risk of unintentional injury mortality as temperatures rise, particularly when daily maximum temperatures are above 25 degrees. A major exception in Jiangsu province compared to the U.S. is that the risk of death with rising temperatures is mainly confined to people engaged in activities other than transport. Since these Chinese cities rarely experience below freezing temperatures during the day, the very low rates of bicyclist and motorcyclist death rates at sub-freezing temperatures found in the U.S. would not be expected here. The difference in cultures regarding vehicle use on holidays and weekends in the U.S. and China may be different as well. U.S. road deaths are substantially higher on Friday and weekend days than other weekdays. In contrast, transport deaths in Jiangsu province are 3% less on Saturday and 6% less on Sunday than on the average weekday. This suggests that vehicles are used less for discretionary travel in Jiangsu province. While the results are correlations with the usual concern that they may not represent causation, the literature on behavior when pollution is higher suggests that people adjust their activities to pollution, and it is common knowledge that they do so in response to the weather. Of course, in those cases where injury risk is reduced because of higher pollution, no one would recommend increasing pollution to reduce injury. Even with major efforts to reduce future warming, and particularly acceleration from feedback effects, the coming years will be warmer than any in human history. Without increased preventive efforts, warming is likely to lead to more injury deaths. To reduce non-transport deaths related to injury, we need more research on what people are doing in reaction to the temperature that increases their exposure to damaging energy exchanges. Thank you again for the opportunity to discuss these findings with you. I'll appreciate any comments or questions.